I called my talk Mathematics and the World because I want to discuss a subject which is not really a subject. It is very common to speak about pure mathematics and applied mathematics. But when you talk to mathematicians, for example, they say that this does not exist, this distinction does not exist. And if you think for a minute, you know that at least something exists which you can call application of mathematics. Mathematics can be used to, let's say, to know what will be the result of next elections, to predict with chances of success, results of next election, or even to send rockets to the moon or further, or to make war. Okay, so I resume this in the title Mathematics and the World, insisting in the title of my talk, in the world, and we had a discussion with Lena about, because I wanted and to be in fact, because in the expression mathematics and the world, I don't want to define what is the world, and I don't want to define what is mathematics. I want to think about the connection. Okay. And my talk can be symbolized by a proverb which comes from very old Chinese philosophy, philosopher called Chuang Tzu, who would say, I translate from the French because I have it here in French, everybody knows the utility of what is useful, but nobody knows the utility of what is not useful. And this applies very well to mathematics and the fact that nobody really thinks seriously about it. So I'm also quoting a famous mathematician, quite famous, not so famous, Leon Liechtenstein, who died in 1933, and he used to say, there is no applied mathematics, but only mathematics and application of mathematics. But this man was really an incredible man, because he was for years employed by the Siemens factory as an engineer theoretician, and successfully later on he used mathematics in the theory of planet shapes to describe the shapes of the planet. So Steinhaus, quoting Liechtenstein, who was his professor, said his opinion should not be disregarded. So there is application of mathematics, and also I will try to insist in my talk on quite many mathematicians who have skipped from one field to the other. So there is no field, there is no philosophical distinction between something which is pure and something which is not pure or impure. We will see in a minute, because I will take example from old history. And here I give you, I like some of these funny stories. If you look in the Google, the following sentence: there are problems that mathematicians ask themselves and problems that are naturally asked. I don't know how to translate that. Il y a les problèmes que certains mathématiciens se posent. There are problems that mathematicians ask to themselves, pose to themselves, and problems that appear by themselves, that are asked by themselves naturally. Les problèmes que certains mathématiciens se posent et les problèmes qui se posent. If I quote this sentence, it's because in Google you will find it with the author Poincaré. So I wanted to check where it is in Poincaré, and now I can show you Poincaré, who is, we could say, one of the last. Thank you very much. I can show you two photos of Poincaré. Great guy, great man. There are two, yes, one and the other. You can show the second one. Thank you. Here it is, Poincaré. So Poincaré is considered beginning of the 20th century, is often said to be one of the last men who could envision completely, the whole domain of mathematics. And in particular, he did things in both directions, theoretical, pure mathematics, and applied. And this sentence that I was mentioning was quoted on Google in many places as from Poincaré, but I couldn't find it, so I asked the specialist, what else can I do? I looked in the books, I asked the specialist, and the specialist said that they thought it was not from Poincaré. So let's decide it is not. It could be, but it's not. So from now on, we take applied mathematics in the following sense: mathematical production, starting from an original source, a phenomenon outside of the system of mathematics by itself. The study of the phenomenon, the analysis or prediction of its future evolution may rely on an existing model or stimulate the creation of a theory. So I have listed a certain number of examples. For example, if you try to understand the movement of planets, then it's applied mathematics, but it creates differential and integral calculus. It's a famous story of Newton and Leibniz. The case of electromagnetism, then there is no model, and it was built on purpose to understand electromagnetism with Maxwell and others, and then it led to many difficult problems of mathematics. And at the opposite, the current situation of, let's say, molecular biology or the neural system of the brain, where there are no models, so you have a kind of a question which is posed by these domains of science, where they would ask for mathematical help, and they do not exist. Okay, so what I want to say first is that this distinction, there is a distinction that existed in antiquity, and I have quotation that I will not give here, but I could give if you wanted, from Aristotle. Aristotle suggested that inside of mathematics there would be sectors or parts that are subordinated, that are slaves to arithmetics and geometry, but they are not arithmetics and geometry. And he was meaning, if people agree on this, that they treat the same object as mathematics, but realize insensitivity object, and he gives examples of what he means with optics and music. So optics and music are these kind of parts of mathematics, but applied, we would say.
Is that Poincaré?
Here.
Poincaré.
No, this is Aristotle,
okay,
already.
Me, sorry.
So this distinction exists already. If you want to see it, it exists already in Aristotle. And some thinkers later on, like Pythagoreans or Proclus, want to distinguish sectors of mathematics following the intensity with which they come close to, I don't know how to translate, le sensible. Sensitiveness, sensitive. So how close they are to le sensible? They are closer to le sensible than they are what we would say more applied. And then, little by little, this distinction developed, and at the beginning of modern times, of course, what we consider like the beginning of modern times is the appearance of Cartesian discourse, and Descartes claims that our knowledge obtained through the power of mathematics will allow us, also here I have no translation in English, de nous rendre comme maîtres et possesseurs de la nature. To make of us masters and possessing nature. So its idea of mathematics also makes us powerful. But what is interesting is that approximately at the same time, there's a new term that appears and which will be later replaced by applied mathematics, and it's the terms of mixed mathematics. And this term appears essentially in the text of Roger Bacon. And I quote here Bacon close to Descartes because it seems, at least it's a hypothesis, I'm not enough familiar with philosophy to judge, but that Bacon played an influential role in the introduction. This is clear. He played a very important role in the introduction of the term mixed mathematics and in a new classification of sciences that he introduced, very subtle and complex, and at the same time that he was influencing Descartes. When Descartes announced the practical use of mathematics, people have said that it was under influence of Roger Bacon. So this has to be verified, but it's an opinion for which I have also quotation of philosopher. But however, in the 18th century, mixed mathematics was still existing, even in the encyclopedia of Diderot and d'Alembert, but little by little it was replaced by applied mathematics. And now if you look at the 19th century, then the whole story of applied mathematics in 19th century has to take into account, first of all, the mixture of these domains together. And as an example, if you want to see how both fields of applications and mathematics for themselves are mixed together, the best is Felix Klein, for which I have no photo, unfortunately, who was born in 1849, died in 1925, and he worked together in both fields and was very active in propagating both fields at the level of education. And I have many examples of the activities of Felix Klein and seminars around 1902, 1905, where he was studying hydrodynamics and focusing on turbulence and practical application, but also using very high-level elliptic and functions and automorphic functions to solve concrete problems of shape in the liquid and movements and things like that. So this is a brief history, but this brief history has kind of stopping in the beginning of 20th century, so I will try to give in 2 minutes the idea of what happened. Essentially, yes please. So you have a strong development, of course, of logic and pure mathematics without any care of the use of it in practical and daily and industrial sense. With the symbol that I took to show this period is, of course, Russell, but I could have talked to you about the birth of set theory, which showed a real breaking in the history of mathematics. And then later on, of course, the appearance of Hilbert, and later of, let's say, the structural school of mathematics represented by Bourbaki, who created a strong cut in the two separate activities of mathematicians. But I don't want to go deeply into a complete history of mathematics. What I want to do is to give some examples. So I will give 2 or 3 examples of mathematicians who went from one field to the other, and mathematics who show the deep unity of mathematics just in the facts themselves. So the first example that I take is connected, the examples that I will take are connected with the hydrodynamics. In fact, essentially, I was thinking I would talk to mathematicians who are gathered for a seminar in homage to Arnold. And Arnold also has been one of these mathematicians who has been doing mathematics on the left hand, very abstract and pure, and on the right hand, interested in systems of planets and hydrodynamics. So I decided to take the example of hydrodynamics. So let me of course, I will not take, even from my personal small point of view, the example of hydrodynamics in the whole. So let me take the example of Navier-Stokes equation. So the Navier-Stokes equation has a history. It was introduced in the middle of 19th century in the study of fluids in order to take into account the viscosity of fluid, which causes at a microscopic level a dissipation of energy. Still, very little is known on the solution of this equation. In general, it's formulated in popular magazine and by the term turbulence. The term turbulence is very important. The idea of turbulence is very important because if you could master turbulence, then you would have no more problems with a lot of things like control of boats' movement and planes. There would be no catastrophe with planes, for example. Very little is known, to the point that it is frequently asserted that the last solid results on the topic, even though hundreds of people are passing theses on the subject, maybe not each year, but dozens each year, and are working on it, the last solid results are those published in 1934 by a man of whom I will say a few words because it is really an incredible story inside of mathematics. It's the results of Jean Leray. Leray was, in few words, he was professor, he was born in France, did École Normale Supérieure and did a thesis with a mathematician who was specialist in mechanics. And his first work in 1933 aims at understanding the shape and, I will say in French, l'allure des tourbillons que le courant d'un fleuve crée en aval d'une pile de pont. When you have a bridge, in the back, if the water